Hi. The last time we derived the equations of motion for the accelerating gravitational field, and actually the solutions of this field is about the rate of the expansion of the universe, which actually determined by the cosmological fluids and the matter densities, because there are fluctuations in space. And actually we were worked in the Friedman-Robertson-Walker metric, which actually the flat space, or actually there are three kinds of solutions in the FRB cosmology, which the flat case and the open and closed cases are occurring in the same time. So for the sake of those cases we are intended to investigate to be easy, for the simplicity, we assume that universe to be flat, and we derive the equations of motion by observing the nearby galaxies around us and their behavior in the accelerating fields. Accelerating field means now actually non-stationary gravitational fields, which are actually not conservative anymore. So the masses inside of the given region, which is actually surrounded by the surface, which the surface itself is determined by us, so as to evaluate the behaviors of the galaxies which are embedded and bound into the gravitational potential, is actually what the Gaussian surface of ours is. And actually this is, we integrated this surface and the embedded volume from all the entire space. And we defined that the gravitational field is about to be accelerating. But for the sake of the simplicity, we assume that for the first time, it was actually the stationary gravitational fields, and afterwards we defined the equations where the radius of the Gaussian surface, which is actually this pair, was increased as the time itself elapses. So the time is the process that you are observing some manifold in space, right? Those are actually the coordinates. So we did the FRB cosmology actually. So the flat case was our case actually, and what we deduced actually, that we derived the equations of first order Friedman equation. That was actually the main problem. So the second order actually we afterwards did, and it was actually the minus sign there, and which is actually corresponds to the effect of the gravitational attractions, which is actually the opposite direction of the acceleration of the universe, and which tends the universe to be slowed down. And we actually found that the density and the ratios, all the densities of the different kind of materials inside of the universe, Michelinius contributions, are varying as the universe itself expands. So those were actually our cases, right? So today's very auspicious intentions of ours is to derive the second order Friedman equation by using the other mathematical tool, and which is actually derivation. So there are no physics that much, but I will, it's my real pleasure, by the way, that I intend to talk about some revision with the other previous cases we did here too, and I want to elucidate them again and enlighten. So let us start, and let me check if it is not recording. And yes, it is recording, not to worry about that. Okay, so in the first inflationary cosmology video, we defined the first order, and by the way, afterwards, the second order Friedman equation, right? And if you have completed the full entire video, then it should not be something different or strange to you. This is something justifiable, so as to understand the behavior of the universe, and which is actually the FRB cosmology, which the universe itself is homogeneously distributed along all directions, so this is isotropic. Okay, so we have found that the Hubble parameter, the function, not a constant, which is actually known as the constant, but it's not constant unless you have some defined time, some chosen time, because we want to calculate that, which were actually 8 pi g divided by 3 rho, which is actually the density of the material, right? You put in minus kc squared divided by a squared of t. Is it clear? Well, the K in here corresponds to the flatness, the curvature of the universe, which is actually determined by the Ricci tensor and the metric tensor of the universe. Because in the later videos, we will define the metric, well, because it is the variational calculus, and which is actually ds squared. Well, we call it, well, it can be d tau squared, the propel time, or whatever there is. So it can be, well, let us write down this one for the first time. So ds squared is the geodesics, which corresponds that the possible shortest straight line between 2 points. Well, it can be the longest one, but the important is that it is something straight as possible as it is. The importance is that ds squared is, for example, you have some coordinates gmn. Gmn is the dummy indices actually, which is actually second order covariant tensor, and gmn, well, let's say dxm, dxn. So we will use many properties of this afterwards, this case, because this case is not included in the is not included in the curvatures of the universe, which corresponds that the k equals 0 in this calculation. So there is no need to use geodesics, by the way, but if you want, then you will be my guest. So actually those are the other videos, topics, actually maybe 3 or 4 afterwards the videos. So for example, it can be proper time and proper initial time, for example, proper time and initial time, plus the space components. Well, actually something like this. But it depends on the event to be space-like or time-like event. Separation actually. dx m squared. Okay, so m equals, well, let's say m equals 1. Well, not 1. 2, 3, and dot dot dot. So it's actually the dimensions of the space that you are working in. Okay, we are writing down, and by the way, the important thing is, well, you are actually some vector in Euclidean space, and you have another vector in Riemannian space, which is actually the curved space. So you just transport this vector in both frames of references and both spaces. So the vector will not be the same. So it will be changed, which is actually the parallel translation of the vector. Okay, so the vector will not change, for example. So for example, if you have some vector in here, let's say dA with components n, then it will be not the same as the other vector. And there are some variations which are actually coming from the coordinate transformations and which are actually coming from the vector itself changes. So both of them contribute to each other. So we have Neve operator, Neve derivation operator, and which is actually the variation an, and which is actually dan minus gamma. Well, this is actually the Christoffel symbol, and which is let's say mr ar dx. That's the easiest one. This is actually rank 1 tensor. Okay. Well, whatever that is, it's visible. The important thing is that, and I'm happy to see that if it is visible. And as you can see, if the k equals 0, then it's going to be the straight, not straight, come on, the flat universe. There are no curvatures, but in fact we have to add them, which are actually the consequences of the Friedmann-Robertson-Walker metric, 3 plus 1 dimensional space. We will use a spare as a tool. So by using this equation, well, it was actually a dot over a, which is actually the time derivation respective to the time. So I intend to derive equations where the second order equation is needed. Well, why is that justifiable? Well, why is that useful? I mean, what are those benefits of this second order differential equation of Friedmann metric? Well, because why? The second order Friedmann equation includes the energy densities, but not the curvatures, because the energy density itself includes the curvatures too. So, for example, if you have dark energy, which is actually the positive effect towards the expansion of the universe, so the radius of the universe is being accelerated and increased by a factor. It's the factor is actually e to the infinity. well, e to the h times t. So h, well, it's actually this h, and which is equals, well, 8 pi g rho vacuum. The vacuum is the vacuum energy in the universe. So, well, if it is dominant, well, and for today's universe we know that this energy density is dominant, then this thing, well, how much, I mean, the ratio is about infinity, so big, so enormous it is. And so this goes to 0, is a large number. And, well, we neglect the contribution of the time. Well, the time, as the time goes infinity, which is actually the future times, then this thing is diverged, right? This thing diverges. So this is infinite. And for example, in the previous video, we derived the, well, very relation that the matter density of the universe is decreasing by a factor of the scale factor and a cube, the third cube, right? And actually those are the scale factors of the universe. And we found, well, maybe not yet, that a of t equals t to the 2 over 3. For radiation, it becomes the 4th order of scale factor. Well, so it decreases more rapidly than the matter energy density. So which is about, for radiation, a of t equals t to the half. Okay? For mixed case, actually, it's actually the same thing. Well, the radiation-dominated era of the universe is, for the assumption of our case, that it starts from the Big Bang singularity, which t, the time, is equal 0, and which actually the amount of time that is required for the dominance of the radiation density in the universe, which distributed homogeneously, by the way, is about 70,000 years, plus or minus 10,000 years, with some uncertainty, okay? And afterwards, the material, the massive material, has been formed, and well, those times actually what we call the mixed case, where the radiation and the matter densities are together. So the mixed case will be the summation of those contributions, by the way. And afterwards, the radiation becomes less important and the matter grows because of the stars and the galaxies that they are forming and the consequences of their presence in the universe is the other stars and their interactions with the gravitational attractions. The key point is that the gravitational attractions of the universe. Yeah. Gravitation tends the universe to be slowed down. Why? Because this is something attractive, yeah. For if you don't study the negative pressure, then yeah, it's supposed to be for the classical theory and by the way the relativistic theory that it should be. But what we do in relativity is actually not the field. Well, we are not investigating the field by taking care or taking a look into the material that caused the field around it, but unless, instead of this case, we are interested in the energy densities that are actually producing that the space-time is being curved and bending over. But what we know, as the universe expands, the material inside of this universe, and by the way the space-time is being deformed and stretched out. So the materials inside of the universe are just being stretched, and their atoms, imagine every particle which are making up the whole energy of the entire system is being pulled. No, pushed. But the interactions of gravitational field, the presence of the gravitational material inside of the Gaussian surface that I myself desirelessly choose so as to understand the behavior of the given particles in the boundaries which are embedded in each other, are just interacting. Inevitably they are. And by the way, we actually ignore the contribution of the space-time difference because of this separation. Otherwise, the events will be space-like events. So the observers cannot deal with time. Because as the space components between two frames of references or two observables are getting larger, then the synchronized clocks will not true anymore. This is just an assumption for classical theory, because as the distances are increased, time intervals will be increased too. So the physics must be the same physics, but the interactions, as the classical theory predicted, will not be happen in the same time, instantaneously, okay? It will take time to travel the information from this place to this place. So the observers will not deal with each other. So there's a phase, something like the phase, yes. But we are explaining this phase in the relativistic notations, which are actually space-like events, time-like event, or maybe light-like, null ray event. Okay? Okay, what I was talking about was that the gravitations and the gravitational attractions of the universe are just tending to the universe to be slowed down. And I'm going to define that the effect of gravitation is actually it's validated actually by the second order Friedmann equation, which we intend to derive. I hope I can start. Well, those things are amazing and assiduous, are not they? Elegant, right? All of them. Okay, so those are actually miraculous for me. Well, this is actually 4 pi g divided by 3 rho of t and a of t. This minus sign corresponds to many things inside of this equation, which is actually the opposite direction of the acceleration, because the a double dot is the acceleration of the universe. So are we recording still? Yes, we are. Alright. Okay, so this was actually my first order differential equation for Friedmann equations, and I'm going to take a first time derivation of it so as to find out the second order differential equation. So let us write down all terms, so which is a dot square, respectively of the time, the functions of time, a squared equals 8 pi g divided by 3, well, g and pi, all of them, you know that, we assume that, otherwise it's all meaningless, rho of t minus kc squared divided by a squared of t. So I multiply both sides with a squared of t, so as to find out the very solution of, well, actually I want to see that relation of the a dot squared, okay, because I intend to derive it respectively to the time. So I multiply both sides with a squared, so a dot squared, I'm not writing down, well, okay, I'm going to write down this, 8 pi g divided by 3 rho of t and a squared of t. And they will vanish in here, minus kc squared divided, well, okay. Is it clear? Well, you can't say anything. Sorry. Okay. So I intend to take the first time derivation of it. Okay. So the d by dt, well, this is actually the operator. It's the time, and we are not actually looking forward for those operators to be commutative with each other. They commute with each other because we are not studying quantum mechanics right now. Every physical observable in this dimension, not the dimension, in this place, let's say, are commutative, and for example, time operators, because we are not doing quantum mechanics right now, so we are not in that very position to investigate, afterwards infer with some great auspicious assessments to operators that are they commutative or not. Important is that they are right now. Okay, you can use many theorems to prove that. All right. So d by dt, by the way, I'm going to derive the whole equation. So, okay, let's say a double dot, right? The left-hand side, and the right-hand side becomes 8 pi g divided by 3. I'm going to write down in the parentheses that rho dot a squared of t plus rho of t and 2a of t, a dot of t. And there are no contributions coming from here, okay? We don't actually investigate that the parameter of the curvature is time dependent. for now. Otherwise, it can be something like this. For example, you have some vector ei to the k, and which are actually the parametric vector, right? The xk. So k is actually the components of the space, the n-dimensional n components of space. Okay, it can be. But this is actually the Ricci tensor. Okay, it's getting larger afterwards. We are just going to derive the equations of it. Well, I'm going to sit because otherwise this place will not be visible anymore. Alright, so what we can see in this equation, that there are rho dots in here in our equation, and a dots, right? And there is nothing important there much. Okay, so if you put anything, by the way, we are actually looking forward that material densities right now. I'm going to derive the equations. By the way, afterwards this calculation, we will be able to understand the relation or the requisition of this theory, that this Inflationary cosmology for flat universe does not include the contribution of the pressure on the space-time. So which actually takes place in here, the both cases in here. For example, we have found that the matter density of the universe, for example, take that. There is nothing we can do for this. Well, not the French guy. I like that guy by the way. He's a handsome man and cool. Okay. In here, there is nothing more we can continue to our equation and our process. So I intend to do something that's rho mt, rho sub m stands for the matter density, and rho is a whole density actually. Okay. So this is rho m0 divided by a cube of t. We have found that in the previous video, inflationary cosmology. So the first time derivation of it, respectively to the time, will be minus 3 rho m naught divided by a to the fourth of t times a dot. Is it cool? Well, this thing is enough. I intend to show something more, that it can be written in terms of the Hubble function. For example, the function of Hubble can be observed. For example, in 2013, the Planck satellite observed it that it was something about 67.8 kilometers divided by seconds megaparsec, something like that. I am not sure. For example, so if you put that and you can calculate it. By the way, if you can calculate this, you can find out the whole lifetime of the matter-dominated universe, and the same as the radiation or the mixed case. The important thing is that you have to find out the scale factors and their dependencies. And this is actually the topic of the second video of this course. Okay, let's say minus 3 rho m naught a dot over a and 1 over a cube. So this thing is actually the Hubble constant, right? And here, rho m naught divided by 1 over a cube is actually the rho of t. So which can be written in terms of minus 3 h of t and rho m of t. This is actually valid too, but I intend to use that. Why? Because a dots in here, when I put those equations into here, will be vanished with the left hand side and the other side. Okay, so I am writing down the equation again. 2 times a double dot equals 8 pi g divided by 3. So rho dot, what I am writing down in here is actually this one, parenthesis, rho m naught, minus 3 rho m naught divided by a to the fourth of t times a dot of t times a squared of t. Okay, plus rho of t. Well, we have chosen that the density of the universe, well, so as to find out this and so as to test this, we are actually examining this equation. It was actually matter domination, so I'm writing down this thing into here, rho m naught divided by a cube of t, and times what is there more? to A of t, A dot of t. Okay, yeah. So two things will vanish, and what left behind? Oh, okay. Those things can be 2. So A double dot of t equals 4 pi g divided by 3. So there, well, they will be vanished. 2 minus 3 rho m naught divided by a squared of t. Well, a is all gone. Plus rho m naught through rho 2 times rho m naught divided by, those things will be gone, a squared of t. So here is it possible? Are you seen here? Okay, you are. Okay, good. Those things will contribute, which is actually the minus sign, and I'll put it here, minus 4 pi g divided by 3 rho m naught divided by a squared of t, which is actually a double dot of t. So I can write this term as this one. So I am multiplying both sides and dividing to a of t, the scale factor. And what I get, minus 4 pi g divided by 3 rho m0 divided by a cube of t and a of t. So here is rho m0, rho mt, which is actually the functions of time. So a double dot of t equals minus 4 pi g divided by 3 rho mt a of t. This equation only holds for the matter density, not for radiation density, because these equations, the Inflationary cosmology, we assume that the universe is flat and, well, it can be closed or open geometry, by the way, but there are no pressure terms inside of this space. When you put the radiation, it will be inconsistent with second order Friedmann equations, which are actually 2 times larger than that. I proved that in my video, which I have recorded in school, and it was actually on the chalkboard. I will do that maybe another time. This is just the examination of Friedmann equations by using the first one and to get the second order Friedmann equation. So it is consistent with that. It's supposed to be, because this is non-relativistic matter with no pressure on the space, no effect of pressure. Thank you.